In this video, we are going to discuss about three-phase transformers, where in three-phase transformers, we are going to do construction and operation of three-phase transformers, and later on do calculations on the three-phase transformers. To start with, we do the introduction to three-phase transformers, where in three-phase systems in three-phase systems they were used to generate and transmit electrical power, as we had seen. So three-phase systems, they are used to generate and transmit electrical power. In three-phase systems, we performed measurement of electrical power and what we use in three-phase systems to calculate the power. So coming to our three-phase transformers, which is our topic today. Three-phase transformer, they enable stepping up or down of three-phase voltages and currents. That is the main purpose of three-phase transformers, stepping up or stepping down three-phase voltages and currents. That is the main purpose of three-phase transformers. So the three-phase double wound transformers, three-phase double wound transformers are used in power transmission. So the double wound transformers are used in power transmission. So for your revision, you go and state and explain the advantages and disadvantages of three-phase transformers. That is for your practice. You go and state and explain three advantages and disadvantages of three-phase transformer. So under the construction and operation of three-phase transformers, I've done the introduction. Now going to our lesson today, the construction and operation of three-phase transformers. We have types of three-phase transformers. We have types of three-phase transformers. And in this, we want to see how the three-phase transformers are built. Number one, you can build a three-phase transformer. You can build a three-phase transformer using a bank of three single-phase transformers. So in this case, you have three single-phase transformers. That's how you can build a three-phase transformer using three single-phase transformers. Using three single-phase. You have three single-phase transformers. Three single-phase transformers. Number two, by constructing a transformer on a common magnetic structure, you construct a three-phase transformer using the magnetic structure. We are going to do details used to see how you can build a transformer using the two methods. So number one, using a bank of three single-phase transformers, using the bank of three single-phase transformers. Using the bank of three single-phase transformers, three similar single-phase transformers can be connected to form a three-phase transformer. You can connect either in a delta or a star connection. In a delta, that is in a delta or star or delta connection. So you must have similar single-phase transformers. That is the main key. That's the main key point here. Using three similar single-phase transformers to form a three-phase transformer. The primary and secondary windings be connected in star or in a delta arrangement. So the primary and secondary windings of the three single-phase transformers can be connected in either a star or a delta arrangement or in a delta connection. So we have a figure. This one shows a delta star. We have a delta star connection. This is the first one, using three similar single-phase transformers in a star and a delta connection, or you can use this one, the second method, in a star and a delta connection. In the primary windings, we have N1, which is the primary phase voltage. And number two, we have N2, and we have N1. N1 represents the primary phase voltage, N2 representing the secondary phase voltage. So the ratio between the secondary and the primary phase voltage is called the transformation ratio. The ratio between the ratio of secondary phase voltage, the ratio of secondary phase voltage, or the ratio of secondary phase voltage to primary phase voltage is called a transformation ratio, is called a transformation ratio. So that is the one we have just done. The ratio of phase voltage to primary voltage equals called a transformation ratio, denoted by a letter K, denoted by letter K. This one we have, that is K, the transformation ratio, that is the phase transformation ratio of the secondary to primary phase voltages. So moving on to our next point, three-phase transformer on a common magnetic circuit. This is the second method on how to build a three-phase transformer. The second method, using a magnetic circuit, a three-phase transformer using the magnetic circuit or on a common magnetic circuit, on a common magnetic circuit. So you have the primary and secondary windings. This is the first way to connect them on a magnetic circuit. Or when you remove this is a diagram of how it looks like. So when you simplify it further, this is how it looks like. So you have flux flowing. This is you have the first single phase transformer, the second single phase transformer, and the third single phase transformer. So that is the second method. That is the second way of connecting the three single phase transformers on a common magnetic circuit. This is a magnetic circuit. This is a magnetic circuit. So, or you can having the primary and secondary windings. The phi is the flux. This is the flux. That is the flux. The phi you see in the magnetic circuit is flux. That is flux. This phi here is the flux flowing in the magnetic circuit. And then you can also have this one. You can also have this one, this magnetic circuit. The third one, part C. You can have this one. You have the primary windings, you have the secondary windings, and then you have a laminated core, or the three transformers connected in a magnetic circuit. The three transformers of single phase connected on a magnetic circuit. So you have the primary windings and the secondary windings. You can see this from the magnetic circuit we have. So moving on, you have the three transformer connections. This is how you connect the three transformer. You connect a three-phase transformer. You have a line, you have a line, you have a line. Then these are now the transformers. Those are now the transformers. So this is a delta connection. This is a simplified form of version A. This is a simplified version of this one. So you get a delta connection. Then this one is a star connection, but this is the one which is commonly used. The T, it's more or less the same like a T. So, or a pi. So when you see this, this is a delta connection. This is a delta connection. And number 2B, that is a star connection. That is how you connect the three-phase transformer, or that is how the three transformer are connected. Whereby the primary and the second windings can be connected either in star or in delta. That is how we have just seen. So the four most common connections are either a star or a star to star. Star to star, you have a star to star. The first one is star to star, then you have delta to delta, then star to delta, and delta to star. Those are the main connections that are used in connecting a three-phase transformer. So it's not necessarily connecting in a star delta. You can connect in a delta star, a delta to a delta transformer, then a star to a star connection. Those are the main common connections in three-phase transformers. The primary line voltage is V, the primary line voltage V, and the primary line current I. Sometimes denoted as VL as the line voltage and IL as the line current. Those are the primary line voltages and the primary line current. So we start with the first connection. Out of the four common connections, we have a star to a star, a star to a star connection. This is how you connect a star to a star. This is a star to a star connection, star to a star connection. So when you connect a star to a star connection, shown in here in our figure 4.4, there is an allowance of 57.7%, that is 1. 57.7% is the same as 1 over root 3. 1 over root 3. That is the same as 57.7% of the line voltage. That is 57%. That is 57.7 of the line voltage of VL. 57.7 of VL of the line voltage is impressed upon each winding, but full line current flows in each winding. So you have a full current. You have a full current flowing here. You have a full current flowing, but a 57.7 of the line voltage flowing. You can see that you have a full current, but a 57.7, that is 1 over root 3 of the line voltage flowing in the first connection. So in power circuits supplied by a YY bank, that is a delta, a star to a star, often create serious disturbances in communication circuits. That is a disadvantage of star to star connection. That is that it creates disturbances in communication circuits. That is a disadvantage of having a star to a star connection. Moving on to our second connection is a delta to delta connection. This is a delta. You have a delta to a delta connection. A delta to a delta connection. A delta to a delta connection is used for moderate voltages. A delta to a delta is used for moderate voltages. So an advantage of using a delta to a delta connection, an advantage of using delta to delta connection is that if one transformer gets damaged, for example, if you have the one transformer damaged or removed from service for maintenance, the remaining two can be operated in what is known as an open delta or a V2V connection. So when you remove one transformer, you only remain with two transformers. That is when you have three similar single phase transformer connected. So when you remove one transformer from service, or you are removing one transformer from working, or the transformer gets damaged, the two remains operating, and when the two remain, they can be operated in what is known as in an open delta or a V2V connection. By being operated in this way, that is in an open delta, the bank still delivers three-phase currents. The bank means three similar single-phase transformers. They deliver three-phase currents and voltages in their correct phase relationship, but the capacity of the bank is reduced to 57% of what it was with three transformers in service. Yeah, you can see that. Then moving on to our next connection, that is a star to a delta connection. Star to delta connection. This is a star to delta connection. You can see we have a star and the delta. So the first is a star, and then you have a delta. The first one is a star, and the second one is a delta connection. This one, when you have a star to a delta is used for step down. Star to delta is used for stepping down high voltages, stepping down high voltage. So the primaries are designed for 57.7. 57.7 we have said is 1 over root 3. 57.7 we have said is a 1 over root 3 of the high tension line voltages. So 57.7 being a 1 over root 3 of the voltage. So it gives you a V over a root 3. A V over a root 3. That is what you see here. So the advantage of a star to delta is it steps down high voltages. Moving on to our last connection. From the four connections, we have a delta to a star. You have a delta to a star connection. In this, it is used to step up. high voltage. It's used to step up high voltages. You can see here we have a delta. I have a delta. Then the second one is a star connection, a delta to a star connection. So a delta to a star is used to step up. Step up. It is used to step up high voltages. Used to step up high voltages. So that is all about the four connections. So we had the first connection, we had the first connection. The first connection was we had a star to a star. Then you had a del. The first one was a star to a star. Then the second one was a delta to a delta. That is the second one. The third one, we had a star to a delta, a star to a delta. And then number 4, you have a delta to a delta to a star connection. Out of the four connections, we have seen the third one, which is a star to a delta. It is used to step down. It is used to step down. It is used to step down. That is a star to a delta. A star to a delta is used to step down, while a delta to a star is used to step up. A star is used to step up. It is used to step up. So that is what we have just learned today, and it's used to step up. That is a connection that is used to step